you're ready. Just go ahead.
So this process is about how we are processing data and making it searchable through the life system. So um, I'll just give an overview of what life is. Life is a search tool where you can search different essays that are generated from links, various link centers. So there are link centers not just from Broad, but there are also Harvard and Yale and other people who are generating data. So Life is a search tool where you can search data from various link centers. Okay, and in the process we have to load L1000 data also. So this presentation is about how we are loading the data, how we are aggregating the stuff, aggregating the data, and indexing it. So, um, um, so, so L1000 signatures are we index the signatures which are gold, um, which are categorized as gold from Broad by Broad, and we make it searchable in the context of other essays. And in the process, what we do is we collect small molecule information, cell line information, and SHR and ACDNA, all the informations that are generated across link centers. So if there is a small molecule generated from Broad and small molecules generated from HMS or ALE, we take the SMILES and standardize it, and that's a different process. So I'll explain that in little more in detail a little later. Um, so so that we can search across different centers. So that's what we would do, and then we are doing now, and then we access the data, metadata, and everything from the Broad API. Broad has so this is just a flow chart to show.
Hello?
Hello?
Can I ask a question?
Yes.
So you said you only store gold data sets. How can we know if a data set is gold or not?
So Broad has an API, and the API provides you some of the fields, and one of the fields is a gold. So they categorize it whether it's a gold signature or not. And I'll show you the API. I think.
What's the meaning of gold?
What's the meaning of gold?
Is it a good data? That means that it's a good data set and the others are bad. I mean, how do you interpret this?
According to them, gold data sets are good data sets that are reliable and stuff. Reliable, I think that's what. Yeah, they pass some type of QC, so those are categorized as gold signatures. And this is classified by the Broad, the data center itself. So I'll just show you the API, how it works, and then that would be it. Just give me some time. I will show you the. I'll go through the slides and later on show you the API so that you can see what fields are available from Broad, and then based on that you can. Okay. So there are Broad provides so L1000 data is provided in two. So Broad gives the data in 4 different levels. So one is raw data, 2 is processed, and then normalized data, and then the signatures. So normalized data is at the digital level, and the signatures are so normalized data is at the replica level, and the signatures are a group of all the replicas together. They make it as a signature. There are 4 different four different levels that Broad provides us, and there are two different ways that you can access the data. One is through API, where you can get the metadata of a signature, like what's the concentration, time point, which well it is, the particular signature is, and all of those information you get from the API. And there is an S3 server where you get all the signatures. So, all the Z scores. So I was talking to you about the about four levels, right? The the level 4 is signatures which you get from the API, and the level 3, which is the normalized data which you get from the C3 server. So C3 server allows you to download the normalized data, and data comes in a single file, which is a GCTX file, and there are some bunch of codes already existing from Broad which you can use to process these GTCX files, and we also use one of those. We use Python and JavaScript to process those GCTX files once we download it, and then put it into a database with all the distal IDs and the gene IDs and Z scores associated with them. So we store that into a table. And then using the and as I said, there is also an API which allows you to get the signature info. So what we do is each signature is a combination of multiple distal IDs. So what they do is, there is, for each signature there are a bunch of distal IDs. Distal IDs are kind of replicas of. So each signature comprises of a cell line, time point, concentration, and perturbagen. Perturbagen in the sense like small molecule, or it can be cDNA, etc. So this comprises of a signature. But so to get a signature, they run the same combination of all of these many times, and then aggregate those values and call them as a signature. Okay, so we get using the distal IDs. These distal IDs, we get the signatures and then associated metadata also. So like the concentration, time point, and other information that we need for the signature, we just store all of those into MongoDB. So this is how a signature will look like. It has a cell line and distal ID and signature ID. It has many more fields. I just put few fields here. So each signature comprises of more than one distal IDs. Okay. So when they call it as a signature, they aggregate all of these values and assign it to a signature. So that's how they make a signature. And as you know, so this is what is obtained from the API. So the signature level information is obtained from the API, and these scores are not at the signature level, but the Z scores are obtained at the distal level. So what we have to do is we have to associate these scores for the distal ID for the signature using the distal IDs. So in order to do that, what we do is we aggregate the information. So we take the average of all the Z scores for a particular gene in a particular signature, and then
Amar?
Yes.
Can I ask a question about the signatures?
Yeah, sure.
So if I understand correctly, is this just a subset of repeated experiments? That's what it is? I mean, because it seems like you have the same cell, just different repeats.
So this is distal ID. So the different repeats are distal IDs, and signature. Okay, let me tell you. So they run the same experiment multiple times to verify if the data they're producing is right or not, and based on that they classify it as a gold signature and stuff. right?
Okay, but why do you call this signature? I mean, this is like some repeat, no? I mean, signature usually we associate with a list of genes or a list of, I mean, I don't see the name, what it implies.
So this is a signature. So sig ID represents signature, and these are not signatures. These are not called as signatures. These are digital IDs. They don't call it as signatures.
Okay.
So if they are repeated more than once, right, they don't call it as a signature. Only repeats are not called as signatures. Signatures are unique.
Okay.
Right? What is
yeah.
unique ID for an experiment?
So signatures is based on genes or on experiment, on cells? What are they for?
A signature comprises of a compound, cell line, time point, and plate.
I see.
Can I try to add something, Mario? So basically, these cells are individual samples, right? And in this particular case, these came from the same plate, but were in different wells. And it was probably the same treatment on one plate. So we have 4 different samples, and then signatures are kind of aggregated information from individual replicates of some sort, either replicates on the same plate or replicates across. Put them together, average expression levels or anything like that, then you call it the signature. Does this make sense? So basically, each of these TIL IDs represent a genome-wide expression profile for us. And then signature ID is the summary of these replicated observations into a single whole genome expression profile.
Great, that was very clear. Thank you.
How does that summarize? Yeah, thanks, Mario. So they give information in 2 different ways, right? So they give the Z-scores at the sample level, and they give the metadata at the signature level, right? So we have to associate both the information to get the values for a signature, right? So when I say values for a signature, I mean values of the gene expressed in the signature, okay? So to do that, what we do is we aggregate the information. So it's just an average. So if there are 3-4 samples for a given signature, we just for a given gene, and if it is repeated 4 times, we take the average of it, add 4 of these Z-scores for the particular gene and divide by the number of digital IDs that they have. So that's how we get the aggregate, and then we combine both the information together to put it into a document. So
hello. I have a question. This is Peter. The same process, I assume, applies to Jaffe's data, the 100 signature for the fossil proteome.
No, I don't think so. I mean, for P100, they give us aggregated data itself, so it's not at the sample level. So the Z-score, the fold change that they give for P100 is not at the sample level. They give us for the individual signature. But in this case, Broad doesn't provide us the individual. So So P100 has a fold change, right? And they measure fold change, and then L1000 remains their Z-score. But what's happening is when they provide data, the data provided for P100 is at level 4, and data provided for L1000 is level 3. Part of the information is at level 3, and part of the information is at level 4. So we don't have to do all of these things to process P100 data. Did you get me? I mean, hello?
Yeah, there. Thank you. I do think level 3 and level 4 are available for the P100. No?
I have to cross-check.
Yeah.
I have to cross-check. Okay, but I'll let you know when I get the chance. Okay. So this is the complete flow chart of how we are processing the data from Broad. So first we download the GCTX file and then parse it, save the Z-scores into DB, and then we using the distill ID that we get from the GCTX file, we query the API, get the signature, and store the metadata for the given signature into MongoDB. And then what we do is when we get the new signature, we also try to see if there are any new constituents that are not in the system. So we go there and then collect the metadata for that constituent, standardize it, and save it into metadata constituent database. And once we have the stored metadata into DB, we take the aggregate scores for on the signature level, and then merge those aggregate signatures with the aggregates from here is merged with aggregates in here, and that's how you get a signature or a data for a signature. Okay, and then we create indexes based using different various other input sources like ontologies and data from other countries available from the signature, and then index those based on the type. So this is how we do the standardization of. We have just mentioned is how we are doing a small molecule standardization. So there are some small molecules that are in Broad as well as in in other link centers like HMS, right? The standardization process for all small molecules have been developed in order to find the common compounds between centers. So this is how we do it. So we collect the smiles from the center and then desaltinate it, and we canonical using tragic canonicalization algorithm. We do the standardization of the smiles, and then we use the PubChem service standardization service and get the CIDs, molecular weight, molecular formulas, and all the other latest stuff for the small molecules. And then based on that, we generate an LSMID and add other descriptors, whether it's a kinase drug or whether it's a MLP probe and all those stuff, and then add it to the data. That's how we do it. And this is how this makes it. So this is how our application works. So this is live. You can type in L1000 and kinome scan, and say if you want to add, like, give me only PDB ligands, you can add PDB ligand, and it filters and gives you all the small molecules which are participated in L1000 and kinome scan assays, and which are of type PDB ligands. So that's how we do it. So we have two types of indexes, like perturbation index and constituent index. Constituent index is just at the level of constituents, and if you want to go for a deeper queries, you can use the perturbation index, and then you should be able to search on the signature level. So you can type in any signature ID, you'll get the information back. And these are all the statistics that we have in the system right now. I'll show you an example of how the system works. So, for example, this guy, right? I have given a broad ID here, right? So this is a broad ID, and I have to specify the source. And you'll see all the assays. This compound is tested. So this is a dapamycin compound, and you'll see all the compounds that are tested, and you can filter the data. So we have added cross filter to it. So when we index, we only take the top 50 and bottom 50 up and down regulated genes. That's why you see two peaks. So one is down regulated peak and then up regulated peak. You can filter further. You can say I only want PC3 data from PC3 cell line, and you should be able to get that. And you can also select other information from here, and then it filters further.
Amar?
Yes.
So there is a time point here. Is this a time series? So you say 6 hours, 24. These are different time points in the experiments. Lynx is doing time series.
There are 2 time points. I mean, there are time points also, right?
I don't know. The other, is it really like a time series, or they just measured it? Different days. We didn't know how to read into this.
Let me show you the API. I think that will make more sense. So there are so for a given experiment has a given signature has a time. So there are different is organized into, and the signature info has the signature level. So if you type in so this is all the information that is available from Lynx Cloud API. So if you can see here, so these are distill IDs, right? These are distill IDs, and this is the cell line. And if you go down, you'll have the concentration time point. There are more. So this is the perturbation time point. See here. So a given signature. Okay. A signature has a distinct time point, cell line, concentration, and perturbation. So there can be multiple time points for the same perturbation. So, for example, if you're looking for, say, Rascovitin or something, you'll get multiple time points in which is tested in different cell lines. So there are also different cell lines, right? So, but it's not like they don't range from 0 to all the way to 24. They are like 6 hours, 24 hours, or something, and 48 hours, 96 hours, something like that.
But it is like a time series experiment.
Yes, it is if I may say, it is a time series with many perturbagen profiled only at 2 time points, but you can consider it as a time series.
And all the metadata standardization is specified here, where you can take a look. And so these are all the fields that are that we index, and that is searchable. So, for example, let me give you one example here. How would this searchable? So let's say this is you can browse. So there are various ways you can search this system. You can just use browse or from here, or you can browse from here. And when you click on this, you will see all the, so what's categorized here is the distinct constituents that are tested in this, for this assay. So this is L1000 profiling assay, which is data coming from Broad for the signatures, and you'll see all the distinct, so these are the total number of compounds that are tested in this assay. I mean, standardized compounds that we have, it may be more than, they might have more than that, but this is the data that we have. And these are the complementary DNAs and shRNAs and the cell lines that we have in our system. As I said, we only index top 50 and bottom 50 up and down regulated genes. So we don't have all the 22,000 genes. We only have like 9 genes. And so you can further click on small molecules and go into the details about. You can see what assays it is tested. It is only tested in L1000. You can further filter here. So. Yeah, so that's what we are doing here in at UM. So this is LifeWorks. You can search. You can search by signature ID, or you can search by compound ID, or anything you like. You should be able to see the results.
Yes, Peter here. I have a question. So this doesn't look so. This I've been looking at the Lynx Cloud. Will this interface you just showed us be also available to us, or will the same sort of data be available in a different interface, or what?
So this is from our internal. So we have a system called Life. So life.ccs.miami.edu is our system. This is not coming from Lynx Cloud. These are two different systems. So the Lynx Cloud is where you get the data from Broad, and LifeWorks is the system where we get data from different centers. So if you see here, if you click on cell-based, you will get all the assays that are tested across Link Center. So and also where they are tested and stuff. So in Broad API, from the API, you'll only get L1000 data, but from LifeWorks, you get all the data from various link centers. So these are different assays that we have so far in the system.
Yes. So what about LifeWorks? Do we have access to that?
Yes, it is all. Yes, it's there.
So why don't you just?
I'll just type in there. I'll just type in on the. Okay, but this is not an update. So right now we don't have everything in LifeWorks, but we'll have it soon. Okay. Any questions?
So this is Mario speaking. So maybe as we go forward, one of the objectives is to summarize different ways to construct signatures. And again, signatures are some kind of summary or integration of individual sample measurements in L1000 assay. And I think if I can just summarize and pull out a couple of pieces of information that Tamar provided us. One is that the way they summarize individual expression profiles into one signature profile is to look at signatures as defined by Broad Institute in terms of all the replicated profiles that belong to these signatures. And then they just averaged individual profiles. So that was one way to define signature. The other way, and again, that's provided by Broad API, is to give identities of 50 most upregulated and 50 most downregulated landmark genes. So landmark genes are genes that are actually measured in L1000 assay. So this is another way to define a signature. And again, these top 50 and up 50 and down 50 genes are extracted by summarizing replicated profiles for a signature in these sets that are defined by API. So these top 50 and bottom 50, the way that Broad extracted these, they summarize, again, in some way, these individual profiles, and then identified 50 genes that are most upregulated and 50 genes that are most downregulated. So these are two ways, basically, of defining signatures based on this data. Next time, we will have go back to another way to define signatures using the same data, and this is a method that Avi Mayan's group, Chanan from his group, has a paper on, and he will present a different way to basically summarize these individual genome-wide profiles, gene expression profiles.
One question. Is there, do you know where we can download the other links data that's not L1000 data?
It's from the center, so if it is from Broad, so there are like various centers, right? One from, most of the data is available from HMS, in the HMS DB, so I'll just send you the link. So I just sent you the link where you can get
Okay.
the data sets.
All right. Thanks.
Any other questions?
Yeah, so this is again Peter. So it looks like the Lynx Cloud provides, a whole lot of like the cell morphology studies and the P100 and the L1000 and so forth. Is that correct?
Yes, that's right.
Okay, good. Yeah.
They provide P100 and morphology, yes.
Great.
So this is Chad Young from University of Washington. I have a couple kind of more detail-oriented questions because I've been looking at the data and I just want to make sure that I understand some things. I sent some to you, Mario, just about the different treatment types and the difference between those. But the other thing I've noticed is I want to make sure, for instance, if I see a -666, is that just missing data?
Yeah, I think that's missing data. For small molecules or like butterbogens, they have -666. Maybe we don't know why they have given that, but we are expecting that that's missing and stuff.
Okay, because I've seen it in, for example, the cell line data.
Yeah, even for perturbagen information, you'll get -6x.
Yeah. Okay.
But all the links compounds are standardized, and those are already available, publicly available. Which means that so for all the broad institute compounds, right? I mean, I'm just talking about compounds. The cell lines are not all cell lines are standardized yet, but compounds are standardized. So if there are missing names and stuff, if you find it on the broad API, you can go to the standardized cell lines links provided from the links, and you should be able to get the names.
Okay. And I've also noticed in, say, the level 3 data, there are a number of just zeros. Do you know if that's missing data or something else?
In the do you mean in the GTCX file you found a lot of zeros? That's what you're talking about?
Yes. I don't know that it's a lot necessarily, but I was looking just at the landmark genes, and some of them, yeah, have a value of 0 for some of the different experiments.
Okay. Those are these scores. I don't think those are missing values or anything.
I was looking at the level 3 data. I would expect some zeros on level 4.
Yeah, the way these measurements are actually calculated, it's fairly complex because of the way that this L1000 assay actually measures expression of 2 genes using a single bead. So they have to go through the convolution step. So it is possible that something went wrong with the measurements, or they didn't have beads. Or
go to the NIH site. I want to show you something. NIH grants. You should apply for this.
So I suspect that this grant story was not meant for us. So Ali, did I hear you? Were you going to comment on zeros? No, I was wrong. So it is possible that there are several situations in which you just simply would not be able to come up with a valid measurement for these genes, and that in these cases, 0 would be assigned.
Okay, I just wanted to make sure that I understood that correctly, and it wasn't somehow you getting an actual measurement of exactly 0.
Right. No, that's. I mean, so these are log2 transforms. So theoretically, it's possible, but I do believe that these are just because something went wrong with the measurement for this particular gene.
Great, thanks.
This is Peter. We have to go. Thank you. We'll look again online.
Thank you.
Okay, great. Well, I apologize for the initial debacle with this sound business. I'm going to investigate what went wrong, if there was another way to do it. In my experience, other systems are not any better. But if any of you guys have suggestions in terms of what technology may work better, we can investigate and benchmark and see how it works. So I would like to.
Can I ask one more question?
Yes.
This is Kai from University.
Go ahead, Kai.
Thank you. So by now we have seen many versions of the links data. For example, last week we saw Avi's group is using the level 3 data to infer both experiment and gene signatures. And then you also talked about the z-scores in the level 4 data from Links Cloud. And then there is also the moderated z-scores that are not yet available from Links Cloud. And then the Miami group is doing their aggregating the z-scores in another way. So at UW, our goal is to infer gene networks. So could you comment on what form of the links data would be a good start for us to look at?
Yes. You know, this, I guess that is one of the reasons for having these discussions is to give you perspective of different groups on what is a good summary of these data that or signature that would be a good starting point. As you know, we have this R package in which we process data also in a different way, which I showed a slide last time about how exactly we constructed signatures. I still think this is a reasonable way to construct it. I think Avi probably thinks that his way is better. And I assume that Amar thinks that his way is reasonable. And I also assume that Broad Institute people have a good reason to believe that their strategy is good. So unfortunately, I don't have the final answer for you. We will have Arvind Subramanian give a presentation on November 25. Unfortunately, his schedule was pretty packed up until that point. But since you're coming to this meeting next week, you can maybe also ask him these questions in person. But
sure, yes, I would ask it again. We are happy to have options and choices, but I was just wondering if you guys have done any benchmarking among ourselves yet to kind of get an idea, the pros and cons of the different versions of the data. So
yeah, so I think Avi did some benchmarking. Channan did some benchmarking to show that his method works well. So that would be that would be the beginning. And Channan will give us a presentation next week, right? So
okay.
He will talk about his method again in detail. And he can then tell you, for example, which controls he uses and that kind of things. I know Chad asked me these questions. I gave some answers, but it will be also interesting to hear from his angle. We will want to benchmark this, and we are going to work on it.
Okay.
And your ideas about what exact benchmarks would be the most meaningful would also be useful. But I think that's a part of this process in which we will come up with something that maybe we can say works best in this specific situation. And again, we worked on this independently as part of this Links Consortium in the pilot phase, but we were not all that much integrating our activities until very recently, until the beginning of this project, which has been going on since the beginning of October only. So we are also in the process of benchmarking between ourselves as well.
I see. Thank you.
All right. Any other questions, comments? All right. Well, thank you all for being there and persisting beyond the first failed attempt to have this going. All right. Bye.
Bye.
Bye.